Welcome to the first final prep video. Today a classic satellite problem that sounds simple but hides a real design constraint. Here is the setup. A satellite communication link uses a geosynchronous satellite located 36,000 kilometers from the Earth stations. The speed of light is 3 times 10 to the 8 meters per second, or 300,000 kilometers per second. We have two questions. Part A. Find the propagation delay in this link. Part B. Is this delay acceptable for voice communication? Simple arithmetic, but the answer explains a lot about why your long-distance satellite call feels awkward and why Starlink exists. First, why exactly 36,000 kilometers? A geosynchronous satellite orbits the Earth once every 24 hours, matching the Earth's rotation. If we place it over the equator, it appears stationary in the sky. That is called geostationary orbit, or GEO. To orbit in 24 hours, physics picks the distance for us. From Kepler's third law, the orbit radius works out to about 42,000 kilometers from the center of the Earth. Subtract the Earth's radius, about 6,400 kilometers, and the altitude above the surface is close to 36,000 kilometers. This is not a design choice. It is a consequence of gravity and rotation. Every GEO satellite, from your TV dish to weather satellites, sits at this altitude. Part A. Step 1. Compute the one-way delay from Earth to the satellite. The formula is simple. Time equals distance over speed. Distance is 36,000 kilometers. Speed is 300,000 kilometers per second. One-way delay equals 36,000 divided by 300,000. That is 0.12 seconds or 120 milliseconds. This is the time for a radio wave to travel from a ground station up to the satellite. And it is a hard limit set by the speed of light. Nothing we build can beat it. Step 2. End-to-end delay. To get a signal from one Earth station to another, the wave goes up to the satellite, then back down. Up plus down equals 120 plus 120 equals 240 milliseconds. This is the transmitter to receiver delay. But for a two-way conversation, we also need the reply. The round trip out and back to the originating station is 2 times 240, which is 480 milliseconds. Almost half a second just for a signal to go up, come down, and return. Part B. Is this delay acceptable for voice? The short answer is no. The ITU standard G.114 sets the limits for mouth-to-ear delay. Under 150 milliseconds, users barely notice. 150 to 400 milliseconds, noticeable but still usable. Above 400, conversations become awkward. Our GEO one-way end-to-end delay is 240 milliseconds, already well into the awkward zone. Add processing and coding delays, and real systems push past 300. The round trip is 480, half a second, which is why news reporters on satellite links always seem to stare into space for a moment before answering. For text, video streaming, TV broadcast, this delay is fine. One direction only, no conversation. For real-time voice, it is a deal breaker. So what do engineers do when they need low latency and satellite coverage? Change the orbit. Lower orbit means shorter distance means lower delay. Low Earth orbit, or LEO, sits around 500 to 2,000 kilometers up. At 1,000 kilometers, one-way delay is about 3 milliseconds. That is the regime of Starlink, OneWeb, and the Iridium phone system. Medium Earth orbit, or MEO, runs around 10,000 to 20,000 kilometers. At 20,000 kilometers, one-way is about 67 milliseconds. GPS satellites sit here. GEO at 36,000 gives us our 120 milliseconds each way. The trade-off is coverage and cost. One GEO sat covers a third of the planet, but LEO needs hundreds or thousands of satellites to give the same coverage. Starlink's 10,000 plus satellites exist precisely to break the GEO latency wall. Big picture. For a GEO satellite at 36,000 kilometers, one way up 120 milliseconds. End-to-end across two ground stations, 240 milliseconds. Round trip including the reply, 480 milliseconds. 3 takeaways. 1. The speed of light is a hard physical limit. No amount of engineering can beat 3 times 10 to the 8 meters per second. 2. Altitude equals latency. Every kilometer of orbit height adds delay. 3. Pick the orbit to fit the use case. GEO for broadcast and coverage, LEO for real-time voice and low-latency data, MEO for navigation where long orbital life matters. Good luck on your final.